Hello and welcome to QFI Core Solutions, Fall 2013. Here's a little bit of a disclaimer. I am currently a student studying for the Society of Actuaries exam QFI Core. These slides have been prepared based upon the model solutions given by the Society of Actuaries. However, they have not been approved or endorsed by the Society. All of the material that I'm using has been taken from the SOA website, with the solutions presented being the model solutions that they've given. I'm merely adding some narration, filling in some of the details in an effort to help myself study and possibly help you do the same. I do not claim to be an expert in this material. As I just said, I'm still studying for this exam, so if you notice any errors in how I'm presenting the material, please let me know. So we'll start with question 1. This question asks us first to describe each of the following: the actual volatility, the implied volatility, and the realized volatility, and identify how they differ in terms of their time period, the number of associated time scales, and their ability to be measured. So we first examine the actual volatility. The actual volatility is the measure of future randomness, how much the stock or the underlying price will change in the future. It's an attempt to predict how much randomness will be present currently. It has no associated timescale that it's based off of, and as we're looking at it in a forward-looking time span. Because it's forward-looking, it's nearly impossible to measure. We have no good, reliable data to go off of. The historical or realized volatility is what we'd probably be using in order to help predict this actual volatility. But apart from that, we have nothing good to go off of. The implied volatility is what the market measures the volatility at. So essentially, how much volatility the market thinks there will be when computing some sort of option price. The timescale for this volatility varies based upon the expiry of the option. And so the same underlying asset could be said to have multiple implied volatilities based upon the option that we're considering, or the derivative that we're considering when computing this implied volatility. It's very simple to compute the implied volatility. We just take the Black-Scholes option pricing formula and back solve out what is the volatility that makes the formula hold true. The realized volatility is more of a measure of historical randomness. The timescale for the realized volatility or historic volatility, it varies based upon how much data we actually use going backwards and will want to consider. We can use this realized volatility based upon a number of different timescales, and we can consider it in a larger time grouping, such as monthly return, or a smaller time grouping, such as daily return. These volatilities change significantly based upon the volume at which the underlying asset is traded, and it becomes very easy to measure the realized historic volatility since we know the exact details of the time scale and the calculation method. Part B introduces the concept of estimating the volatility. We'll want to estimate the 60-day future volatility using historical data. We're going to look at using the ARCH, autoregressive conditional heteroscedasticity model, as well as an EWMA, exponential weighted moving average model, and look at their individual advantages and disadvantages. The ARCH model is an autoregressive model, meaning that it takes its own feedback into its future predictions. The arch model is special in that it uses a long-run mean, sigma bar, in order to help stabilize the predictions of the volatility. We look at the historic data where each of the last n returns are equally weighted, in contrast to the exponentially weighted moving average model. Because these are equally weighted, we see a plateau effect. A couple of the major advantages of this model are that we allow the model to vary its we allow the stock to vary its volatility over time. And so as additional returns data comes in, the model will naturally capture more of the variance through the long-run averages. The model is the formula for the model. The next predicted volatility is a weighted average with alpha weighting for the long-term volatility and 1 minus alpha times the average square return. The exponentially weighted moving average model is very similar to the arch model, in that we still vary the volatility with time based upon the recent returns. However, a key difference between the two models is that this places more weight on the most recent returns, and we avoid a mean reversion. By placing more weight on the most recent data, we're able to avoid these plateaus. However, we lose the ability to be influenced by the long-run volatility. The formula is given by the current predicted volatility is equal to an average of the previous volatility. Note how this lambda sigma squared n minus 1 contrasts with the alpha sigma bar squared, added to 1 minus lambda times Rn squared, so the current return squared. Note how this Rn squared corresponds with the sum of the Ri squareds. We can repeatedly substitute in for sigma n minus 1 squared to collapse this term, and so we see the exponential term. We get out that the current predicted volatility is 1 minus lambda times the sum of lambda to the number of time periods in the past times the return some number of times in the past. And note that similar to how we require alpha to be, in contrast now, we require lambda to be between 0 and 1. Here, we did not have that same stipulation. In Part C, we're asked to identify a common model that combines the features of both ARCH and EWMA. Here, we find the GARCH model, a generalized autoregressive heteroscedasticity model. We are able to specify this model as the current predicted volatility is the weighting of some long-term volatility with the most recent data. And that most recent data is a weighted average between the most recent volatility and the most recent return, or most recent square of the return. And so that is question 1.